Ever wonder how your GPS magically finds the absolute fastest route home? Or how social networks somehow connect you to a friend of a friend of a friend? Well, in this explainer, we are completely decoding the secret architecture behind these everyday miracles: graph data structures.
Here is our roadmap for today. First, meet the graph. Second, graph types and terminology. Third, representing graphs in code. Fourth, traversals, DFS and BFS. And finally, number 5, complexity and applications. Let's just jump right in.
Section 1. Meet the graph.
So what actually makes up a graph? At its absolute foundation, a graph is simply a nonlinear data structure made of nodes, which are also called vertices, and the specific edges that link them together. Think of it kind of like a giant mathematical map. The set G consists of V, representing your physical locations or data points, and E representing the roads or the relationships that connect them.
Take a look at this really simple 5-node setup. You've got your vertices scattered around, A, B, C, D, and E, but they communicate through very clearly defined edges, like that direct link between A and B. It's an elegant, non-linear way to show exactly how data points interact with each other in multiple different directions.
Moving on to Section 2. Graph types and terminology.
To really grasp how these networks function, we need to build up our technical vocabulary. First up is the degree of a node, which is literally just the number of connections it has. You can think of it as a node's popularity score. A path is the exact sequence of edges you have to travel to get from one vertex to another. We also have complete graphs where, you guessed it, every single node is adjacent to every other node. And then there are multigraphs, which might feature parallel paths, or even quirky self-loops that start and end on the exact same spot.
Now, relationships get a whole lot more interesting when we start adding rules. In an undirected graph, the edges are like two-way streets. But in a directed graph, also known as a digraph, strict arrows actually dictate a one-way flow of information. And what if we attach a specific cost, distance, or time to those paths? Boom, you've got a weighted graph.
All right, Section 3, representing graphs in code.
Moving from the visual diagram to the actual technical implementation, how do we cram this structure into our computer's memory? Well, the sequential representation is known as an adjacency matrix. It is basically an n-by-n square grid. You look at the row for your starting node and the column for your destination node. A 1 cleanly indicates that an edge exists between those two specific nodes, while a 0 means nope, no connection. If this were a weighted graph, we would simply swap out that 1 for the actual weight of the edge.
But here's the thing. Matrices harbor a bit of a dark secret. They can waste massive amounts of memory. Imagine your graph has 1,000 nodes, but each node only connects to 1 or 2 others. Your matrix is going to be absolutely flooded with hundreds of thousands of useless zeros. And that brings us to a much better alternative for these situations, the linked representation. Instead of a massive grid, we can just use a sequential list of our core nodes. Each node then acts as a starting point for its own tiny, dedicated list, pointing exclusively to its actual neighbors. No wasted zeros, highly space-efficient, and absolutely perfect for sparse networks.
Which brings us to the absolute core of our explainer. Section 4, Traversals, specifically DFS and BFS. There is this stark visual duality between our two main traversal methods. Depth first search plunges deep down a single branch as far as it can possibly go. Breadth first search, on the other hand, sweeps wide, methodically checking every single neighbor at the current level before it ever considers moving deeper.
Let's break down DFS first. Depth first search is a recursive algorithm that boldly explores as far as possible along a single branch until it hits a dead end. But how does it remember where to go next once it hits that wall? Well, it relies heavily on a last-in, first-out memory structure called a stack to keep track of the nodes it still needs to visit and backtrack to.
It really just boils down to a 4-step loop. First, push your starting vertex onto the stack. Second, pop it off and officially mark it as visited. Third, find its unvisited neighbors and push them onto the stack. And finally, just keep repeating that process, popping, visiting, and pushing until your stack is completely empty.
In direct contrast, breadth first search, or BFS, is an iterative algorithm. It totally prioritizes width over depth, visiting all sibling nodes at the present depth level before moving on to the next. To pull this off without getting mixed up, it actually swaps the stack for a queue memory structure.
By using a first-in, first-out queue, BFS systematically sweeps the width of the graph. You put your start node at the back of the queue, remove whatever is at the front, mark it visited, and line up all its unvisited neighbors at the back. It strictly enforces a level-by-level exploration. It's kind of like watching ripples spread out in a pond.
Okay, finally, Section 5, Complexity and Applications. Let's talk about why this actually matters.
When it comes to performance, I highly recommend taking a mental screenshot right here. Both DFS and BFS share the exact same time complexity, big O of V plus E. They both scale linearly because, at the end of the day, you have to touch every node in every path. But pay very close attention to the space complexity. Remember how matrices cause memory demands to absolutely skyrocket to V squared? Yeah, adjacency lists keep things nice and lean.
Your choice of algorithm completely changes what you can achieve in the real world. You choose DFS to quickly calculate a spanning tree, check if a network is connected at all, or just to see if a path exists between point A and point B. But you absolutely must choose BFS if you need to find the shortest path between two nodes in an unweighted network. Seriously, think of GPS navigation, network broadcasting, or finding the fewest degrees of separation between two people on social media. That is BFS working its magic.
Before we wrap up this explainer, let's actually put this theory into practice. Passive listening is great, but getting your hands dirty is where the real understanding happens, right?
Take a look at this 7-node network. Can you map out its adjacency matrix by hand? If you dropped a DFS and a BFS algorithm right onto node A, how exactly would their paths differ? Trace them out. Once you master this small network, I want you to ask yourself this. How do companies like Google and Meta scale these exact same algorithms to search billions of nodes in mere milliseconds? The math completely holds up, but the engineering is a whole new rabbit hole. Keep exploring, and I'll catch you in the next explainer.